Good afternoon, class. We are looking at section 2.4, limits, algebraic methods, and 2.5, continuity. So we did look at limits of sequences, limits of functions at infinity, limits of functions at finite numbers. We're going to look at algebraic methods and continuity. First, this is the summary we've seen before. A sequence is an ordered list of numbers. Limit refers to the long-term behavior of a sequence. If the limit can be pinpointed as L, we say it converges to L. If it's infinity, negative infinity, or does not exist, we say the sequence diverges. And ultimately, we just plug in and observe. We've discussed a couple of theorems, such as the limit of 1 over n to the power of p as n approaches infinity is 0, as long as p is positive. And the limit of r to the power of n as n approaches infinity depends on the base. If r is between 0 and 1, more specifically between negative 1 and 1 is 0, and if it's larger than 1, it's infinity. So when we add up a geometric sequence, we get this value of a times 1 minus r to the power of n over 1 minus r. And when r is between negative 1 and 1, the same theorem applies. This goes to 0, and it becomes a over 1 minus r. Recursive format for a geometric sequence, the nth term, and explicit format. If we add a constant, then we have a different situation, such that, as an example of that would be dealing with patients and medication, or is the percentage that remains in the body, and C is the amount of constant that is given to the patient at a specific time step, given raised to this formula, where B sub 0 is almost always 0, unless otherwise mentioned. C is the amount of constant, and R is the percentage left in the body. Also, we discussed HA, horizontal asymptote. If you take a limit of the function as x approaches negative infinity or positive infinity, and the answer is L, the line y equals L is called HA, or the horizontal asymptote. And while we are at it, if the limit blows up to infinity or negative infinity, then x equals A is VA, or vertical asymptote. Limit exists if the one-sided limits, that means the limit of f of x as x approaches A from the left and right, are identical. So we have a situation where in all cases, when x approaches A, that means from the left and right, the limit exists and it's equal to L in all cases. So the limit has got to do with near A, not exactly at A. What happens exactly at A here is equal also to L, which gives rise to this concept of continuity. So it's also continuous at A. However, in these two cases, discontinuous at A. At A, f of A has the y coordinate of this dot, which is B. In this case, we are not given. So this is the comparison of the two concepts and the concept of a continuity added to that. With that being the case, I'm going to remind you of the limit laws. We did that in the case of the sequences where n approached A. Now we have a limit of f of x as x approaches A, limit of g of x as x approaches A. If the two exist, the limit of the sum is the sum of the limits. The limit of the difference is the difference of limits. If you have a constant being multiplied by a function, you can take it outside the limit. The limit of the product is the product of the limits. The limit of the ratio or a quotient is the quotient of the limits. Needless to say, the denominator cannot and must not be 0. And this concept of a direct substitution has been discussed. When we have a continuous function, we can plug in. And what we do in general, we plug in and observe. When this limit is identical to the functional value, we say the function is continuous. The function with the direct substitution property are called continuous at A. So let's look at a warm-up example. Now, we're going to use the limit laws. I'd like to remind you how it's done. So the limit laws basically say we have to cut this into pieces. We have 1, 2, 3 terms. Let's do that. So we take a limit for each term. The first one, it's the limit to the second power, and this one, -3, comes out. So the limit law says now we can apply the plug-in in. So plug in 4, and what happens in this case, anytime you have a constant, x approaching any number, 4 or any other number makes no difference, the constant is the answer. Now 4 squared is 16 minus 12, 4 plus 7 is 11. As we have discussed this before, we could simply plug in and it gives us the same answer. So what we do in general is that we first plug in. And we observe. If we get to a number, any number, we are done. Zero over a number, the answer is 0, we are done. Over any number other than 0. If there is some number over 0, we have to figure out if it's negative or positive infinity. Why is that? Because 0 is the only number that when we take a limit from the left and right, they have different signs. The left side of 0 is a negative value. So the left side has a negative sign. The right side has a positive sign. But any other number, both sides have the same sign. For example, number 5. The right side is positive. The left side is positive. Number -2. The right side is negative. The left side is negative. The only number is 0. And finally, when we plug in, we get to what's called indeterminate form. We have many indeterminate forms, such as 0 over 0, infinity over infinity, infinity minus infinity. And that's what happens mostly in calculus. Let's look at this graph, observe, and come up with the answer. We want to come up with the limit of f of x plus 5, g of x as x approaches -2. To do that, first let's use the limit laws to cut this into 2 pieces, and then we take the 5 out. So we do this first. Then we want to come up with the limit of f of x. F of x only as x approaches -2, which is the red function, and then the g of x. So let's look at f of x, everybody. Just the red function. The limit of f of x as x approaches negative 2. Anybody knows the answer? This part? The limit of f of x as x approaches negative 2 equals
1.
perfect. The answer is 1. Let's find out why. So this is number negative 2 on the x-axis. Here's the left side of that. And we are moving in this direction. On the curve, if we're coming from the right side, we are moving in that direction. And whether we come from the left of the graph, of the right side, or the right side of the graph, we are moving towards this hole, which gives us the y coordinate that has the coordinate 1. Therefore, the limit of f of x as x approaches negative 2 is 1. Now, the limit of g of x as x approaches negative 2, we are looking at the blue function, the piecewise defined function. What is this limit? Anyone?
Negative 1.
Negative 1, perfect, because we are moving in this direction from the left of negative 2. We are moving in this direction from the right of that. And in both cases, we are moving towards this point. And this point, what is the y coordinate? The y coordinate is negative 1. Therefore, we're going to replace this with 1. We're going to replace this with negative 1. Makes it 1 plus 5 times negative 1, which is negative 4. We want to find the limit of f of x times g of x as x approaches 1. And again, since we are dealing with two different functions and two graphs, first let's separate them using the limit laws. And let's find each one, this one and this one. So we want to find the limit of f of x as x approaches 1. Meaning we are looking at the red function. Anyone knows the answer? This is number 1 along the x-axis. We are moving in this direction. On the graph, we are moving in this direction. From the right side of number 1 on the x-axis, here's the right side. And coming from the left, coming from the right, in both cases, we are moving towards this point. What is the y coordinate of this point?
2.
It's number 2. Perfect. Now we're going to do the same thing to g of x, the blue graph. We want to find the limit of g of x as x approaches 1. And we notice that what's going on with this limit? The limit of g of x as x approaches 1 d and e does not exist. Why is that? We are going to look at one-sided limit. So g of x is the blue function. So from the left side, we are moving in this direction. From the right side, we are moving in this direction. So from the left side of 1 in this direction, we end up here. And now this point, what is the y coordinate is -2 from the right side of 1. And here's the graph. We are moving towards this hole, and this hole has a y coordinate which is -1. They are not the same. Therefore, this limit doesn't exist. So the product of these two is 2 and doesn't exist, which means that doesn't exist either. I want to quickly show you a slightly different approach which works out in the same manner. And that is, if you look at this one, you write this one and say, okay, now let's look at the limit of this function as x approaches 1 from the left, and then as x approaches 1 from the right. So 1 from the left, you have to multiply this one and this one. The way it works from the left or right for this one makes no difference. The answer is 2. But this one from the left is -2. Their product is -4. This one from the right also is 2, makes no difference, but from the right here is -1. Their product is -2. So this is the limit from the left for this product, and this is the limit from the right. They are not identical, and therefore the limit does not exist. What I want to add here, I want to add 2 more things to make sure everybody is comfortable with the concept, and that is the following. So what is f of -2, g of -2, what is f of 1, what is g of 1? These are precise answers. So for the f function, the red function, we have a solid dot, and therefore the answer is the y coordinate of that, which is 2. For the g function, the blue graph, g of -2 is the same as its limit because there is no discontinuity, and the answer is -1. F of 1, again, it's continuous, so precisely the answer here, the same as the limit, which is 2. G of 1, the g function is the blue function, and you look for the solid dot, and the solid dot has the y coordinate -2. So we want to distinguish between the concept of a limit and the functional value. All right, here's the function, the limit of absolute value of x over x as x approaches 0. This does not exist. Why is that? First, I want to remind you of the absolute value function, which means distance from 0, and therefore absolute value of x is x if x is greater than or equal to 0, and it's negative x if x is less than 0. However, if you look at this one, because the denominator is x, you can't have the equality as you have it here, and that becomes the ratio of x over x or minus x over x, and it becomes either 1 or negative 1. So this ratio, when x is positive, is x over x, which is 1. When x is negative, is minus x over x, which is negative 1. And therefore, they have different limits. If I were to write this for this part, would be x over x, which is 1, or this one would be minus x over x, which is negative 1. So you have two branches, and it is not defined at 0. That's why we have holes here and here. So the limit of this function as x approaches 0, from the left, we are in this branch and it's negative 1. But from the right of 0, we are in this branch and it's positive 1. Since they are not identical, the limit does not exist. All right, so this is understanding the concept and the graph. Let's go look at some examples, again involving algebraic method. So remember the methodology, basically plug in and observe. So if we plug in here, just plug in, what do we get? When we plug in 2, 2 squared is 4 times 2, 8 and 1 is 9. Over here, 6 minus 2 is 4. And square root of 9 over 4 is 3 halves. We are done. So you plug in, you get a number, any number, and you're done. What happens when we plug in here? We end up with 0 over 0, which is one of those indeterminate forms. So what we are dealing with here is what we call a complex fraction. Complex fraction. And to simplify complex fraction, you multiply the top and the bottom by LCD. There are two fractions at top, and the LCD is 4x. We are going to multiply the top and the bottom by. First, I want you to observe what's happening at the bottom. You notice that x is approaching negative 4, and this is x plus 4, and the 0 in the denominator is the one that gives us a hard time. We want to get rid of that. That's why you never ever distribute. You keep it as a product. But for the top, if you do the multiplication, you multiply 4x by 1/4, and you get x. If you multiply by 1 over x, you get 4. And as you can see, there is a common factor of x plus 4. We drop. Again, look at the denominator. We are not going to distribute. So we get the limit of 1 over 4x as x approaches negative 4. It is important to know the limit sign will not go away until now that we are going to plug in. When we do that, the denominator becomes negative 16. So the final answer is negative 1 over 60. The next question, we are dealing with the limit of a rational expression. In general, when you deal with a rational expression or even a fraction, we put it in lowest terms. So that would be the best policy. However, if you don't, I hope you know that you are going to end up with 0/0, and it may not happen always. Okay. So we are going to factor, that is the technique when we deal with rational expressions. We are going to factor the top as well as the bottom. Anybody want to give us the factor form for the numerator? So x plus 5, x minus 5, and the denominator x comes out. We are using difference of squares, a squared minus b squared, which is a plus b times a minus b. X minus 5 is in common. We drop him. And now if we plug in we get 10/5, which is 2. We get 10/5 or 2. All right. Again, we are dealing with the rational expression. And again, if you plug in, you get 0/0. So we need to factor this. Anybody want to give us a factored format for the top? Factored format for the bottom. All right. The top, you take out the x. The bottom, you want two numbers. The product is a c, in this case is -4. The sum is b, in this case is -3. Now, what I want to add is this. First, here's the factored format. The top x comes out times x minus 4. The bottom is x minus 4 times x plus 1. What I want you to notice is this. X is approaching 4. And remember, it is the 0 in the denominator that gives us a problem. So because x is approaching 4, most likely we have the factor of x minus 4 in the denominator. If x is approaching 1, most likely we have a factor of x minus 1 in the denominator. If x approaching -1, most likely we have a factor of x plus 1 in the denominator. That should help you with the factoring. We can drop the common factor of x minus 4. And now if we plug in, we get 4/5. For part B, what do we get if we plug in? When we plug in h equal to 0, what do we get?
We get 0/0.
Beautiful. And anybody remembers the technique for a case like this?
Multiply by the conjugate.
Perfect. And the conjugate, simply put, changes this negative to positive. We multiply and divide by it because we are using a minus b times a plus b, which becomes a squared minus b squared. Now, remember, it is the 0 in the denominator that gives us a hard time. So the denominator, we will never ever touch that. We keep it as a product. The numerator, a minus b times a plus b becomes a squared or the square root of 1 plus h squared minus 1 minus b squared or minus 1 squared. So that's what happens. It comes out as 1 plus h and then minus 1. 1 and negative 1 cancel each other. Again, notice the denominator, we just write it the way it is. We can drop this h. We can drop this h and replace it with 1. And now we replace the h with 0. Square root of 1 becomes 1. 1 and 1 is 2. So the final answer is 1/2, and we are done with this. Okay. So the techniques, various techniques that we should be comfortable with using factoring, multiplying by conjugate, multiplying by LCD to get rid of a complex fraction. This one, if we plug in, what do we get? Anyone? If we plug in, what do you think we get? We get 0 over 0. The technique is like the previous one. Multiply and divide by the conjugate, which means this changes to plus. Again, we're not going to do anything to the denominator because class x is approaching -4. That means x plus 4 is a problem. That means we are hoping to get rid of that. It is the 0 in the denominator that we want to fix. So we just keep it as a product, but the top is a minus b, a plus b. So the top becomes square root of x squared plus 9 squared minus 5 squared, which is x squared plus 9 minus 25, which is x squared minus 60. Again, notice the denominator hasn't been touched. It's just a product of the two pieces. The numerator is x squared minus 16, and by now everybody knows it's a squared minus b squared format, so it's x minus 4, x plus 4, and we can drop the common factor of x plus 4. So we write the rest of them. And again, notice in every step we are keeping the limit until we replace the x. In this case, this one and this one. When we do that, the top becomes -4 minus 4. The bottom becomes square root of -4. Quantity squared is positive 16. And 16 and 9, they add up to 25. And this square root is 5. and we end up with -8/10, which simplifies to -4/5. All right. Here's the next example. I want you to plug in to see what you get. Plug in. Just plug in. What do we get? Anybody has the final answer?
Um, 1/2.
Perfect. When you plug in number 6, this goes to 0. This is 3. You square this one, you get 36 minus 7 times 6 is minus 42 plus 12. Now all you have to do, keep the 3 at top and add up the bottom. Okay, 36 minus 42 plus 12, and you get number 6. The ratio is 1/2, meaning we don't have to multiply by the conjugate. We plug in and we observe, and that's the first thing we need to do. So we have to plug in and observe first and foremost. The next one, if you plug in, you get 0/0. In the same situation, you're dealing with a complex fraction. We are going to multiply by LCD, which is 3x, and divide by it. We keep the bottom as a product. If we multiply 3x by 1/3 gives us x. We multiply these two, we get -3. And now the common factor of x minus 3 can be dropped. So the limit of 1/3x as x approaches 3, and replace the x, we get 1/9 as the final answer. That would be the final answer. We want to look at the concept of continuity. A function f is continuous at x equals a if the limit of f of x as x approaches a equals f of a. What does it mean? Number one, f of x exists, which is the output at a. Number two, the limit of f of x as x approaches a equals L, meaning one-sided limits are identical. Number three, the limit of f of x equals f of a, meaning the limit value and the output are identical. If so, the function is continuous at a. A function is continuous over an interval I if it is continuous at each point a in that interval. If f is not continuous at x equals a, we say that f is discontinuous or has discontinuity at x equals a. So that's the definition. Let's look at a couple of simple examples. And again, I'm going to remind you, if the limit of f of x as x approaches a is equal to f of a, we say it's continuous at a. So the question is, at which numbers is f discontinuous and why? So when we look at this function, we notice that at number 1, we have a hole. So at a equals 1, this is discontinuous because we don't know what's f of 1. F of 1 is not given to us. Needless to say, the limit exists. The limit is whatever the y coordinate is here. The next number is 3. If you look at number 3, the limit from the left and the limit from the right are not identical, so the limit doesn't exist. Number 3 fails to be continuous. Why is that? Limit from the left, limit from the right are different. They are not identical. Number 5, does the limit exist at 5? Yes, both of them are going towards that point. Do we know what's f of 5? Yes, whatever the y coordinate of this one. But the problem is they are not identical. So at a equals 5, the problem is that the limit of f of x as x approaches 5 is this y coordinate, but f of 5 is different. So those are the reasons they fail. Here's a piecewise defined function. G of x is 1/2 x plus 3 when x is less than -2, and it's x minus 1 when x is larger than or equal to -2. Is the above function continuous at x equals -2? Why or why not? Notice they are not asking for any other point. The reason why, because the top piece is a linear function and it is continuous everywhere. The bottom piece is also a linear function. It's just a line. Again, the top is y equals 1/2 x plus 3. The bottom is y equals x minus 1. Each one is a line, and they are both continuous everywhere. So the only problem is the end point at x equals -2. So let's find out what's going on. First, the function value. You look for the equality, wherever is the equality, and you plug in. So equality is here, so this is the portion you are going to plug in x minus 1. So g of -2, this is g, that's why we call it g of -2. You go to this branch and replace the x with -2. -2 minus 1 is -3. Now, let's look at one-sided limit, starting with the left side. If we want a left side limit, that means we want the limit of g of x as x approaches this number, -2 from the left. That's what we want. This is the left-sided limit, -2 from the left. Because this is less than -2, we have to use this function, 1/2 x plus 3, and replace the x with -2 into this function. The product of 1/2 and -2 is -1. With 3, they add up to 2. Let's look at the right side. The right-sided limit is asking for the same thing when x approaches -2 from the right. -2 from the right. Now, -2 from the right, x is larger than or equal to -2, puts us in this branch. See, previously we have looked at graphs. Now we are looking at pieces of a function given. So in this case, we are going to replace the x with number -2. And when we plug in -2, -1, we get -3. So as you can see, the limit does not exist. Why not? Because the two are not identical. The limit of g of x as x approaches -2 from the left is not equal to the limit of g of x as x approaches -2 from the right. Therefore, this limit does not exist. Therefore, g is not continuous at x equals -2. The limit doesn't exist. It's not continuous at x equals -2. One observation which is important to see, I hope you see that this is identical to the functional value. And the terminology that is used is that the g of x is continuous. CTS short for continuous. At x equals -2 from the right. Okay. So this, the answer is yes. And the reason is this. These two are identical. So we do have such thing as continuity from one side. But let alone, is this continuous at x equals -2? The answer is not. No, it's not. All right. Let's discuss types of discontinuities with this example. If you look at this part, if you look at the graph, part A or part C, or these parts, they all have discontinuity, but we want to discuss the types. These two are called removable discontinuities. Parts A and C, these two. This one. Why are these called removable? Because we really have no problem. All we have to do, we could remove the discontinuity by redefining f at just the single number 2. In this case, number 2 has a problem. F of 2 is missing, is not. So if we redefine f of 2 having the same limit as this number, whatever that this is, maybe number 3, then it fixes this problem. In this case, f of 2 has a different value than the limit. However, if we redefine this one, can fix the problem. So fixing the removable discontinuity is easy. In other words, we just have a different functional value, or the functional value doesn't exist, but the limit does exist. So in this case, the limit of f of x as x approaches to exist. So if you look at both functions, this one and this one, the limit is this y coordinate. Whatever you read, that maybe is close to number 3. What about the other two? We can't fix this. There is nothing we can do to fix this. We can't fix this either. This is called infinite discontinuity because it goes, we have a vertical asymptote, and this is called jump. So infinite discontinuities and jump discontinuities, there's nothing we can do to fix the problem. Removable, we can fix the problem. Infinite discontinuity, jump, none of them we can fix. Let's look at this function. H of x is given as such, equals x squared minus 9 over x minus 3 when x is not equal to 3, and it's equal to 7 when x is 3. Is this continuous at x equals 3? We want to look at, if you look at this expression at x equals 3 is undefined, so we have to look at the limit and the functional value. If they're identical, so be it. So you have to take the limit, and because this is the expression, whether we approach 3 from the left or right, it's the same. We can take the limit in one shot. Take a limit of h of x as x approaches 3. So let's take a limit of this top expression as x approaches 3. And as you can see, if you plug in, you get 0 over 0, and the technique is factoring, and the numerator is in the form of a squared minus b squared. So you can write x minus 3 and x plus 3. We get the limit of x plus 3 as x approaches 3. And notice again, we have kept the limit sign. And now we're going to replace it, and the answer is 6. So is h of x continuous? When we look at this one, all we have to do now compare to the functional value. I hope you know the meaning of this is that h of 3 is 7. Are they identical? No. Therefore, it's discontinuous at x equals 3. The limit of h of x as x approaches 3, we proved it to be 6. h of 3 is given to be 7. They are not identical. It's not continuous. However, fixing it, if we redefine this as number 6, we can fix the problem. However, just the way it's given, it's discontinuous.